comments of a kind of general nature, which sort of come from what your funding agent might ask you. You spend a certain fraction of your life working on heavy fermion materials. What's it good for? And so, do we learn anything? Do we learn anything from looking, or what do we learn any general thing from looking at heavy fermion materials? And in particular, my question is, or what I've been thinking about is there some lesson that we learned from heavy fermion superconductors that relates to superconductivity in general? And these particular thoughts that I have on this have come about from discussions with David Pines, Doug Scalapino, and Joe Thompson. And I want to, well, it's a particular point of view. If you look at the whole history of superconducting materials, what's going on from the beginning, the earliest problem, if one says that, was regarded as a very rare phenomenon. And in fact, as time went on, we found out that superconductors are all over the place. And the only systematic that was ever discovered, to my knowledge, before heavy fermions was the so-called Matthias rules, which really only applied to transition metal alloys. There are certain they did not really apply outside of. There were certain electron per atom ratios where transition metal alloys peaked in their TC. So actually, looking for that actually was something that Fermi suggested to Matthias over a tennis game one afternoon. Apparently, he said, everything in metal seems to go like electron concentrations. Why don't you look at that? This didn't really apply to other kinds of superconducting materials. But when we came to the case of heavy fermion materials, it turned out that all the superconductors, as near as we can tell, seem to lie in the vicinity of some quantum critical point, magnetic quantum critical point in this case. But the argument I want to make is that actually, if you look around in the more general, broader set of superconducting materials, so what you find is that, or you can make an argument, that all classes of superconductors seem to involve a phase diagram with a competing localized phase. In the case of heavy fermions, it's some antiferromagnetic phase versus pressure, as shown in this particular phase diagram here. This is actually from Tucson Park. This is cerium, rhodium, indium 5 under pressure. But the important point here is, or to me, the interesting point here is that when the antiferromagnetic phase boundary intersects the superconducting phase boundary, then in fact there is no, that the magnetic phase boundary does not extend into this superconducting side. Namely, that superconductivity actually takes out the antiferromagnetism. And the way to, or the simple way to think about this is in fact that the superconductivity gas out the low energy magnetic fluctuations that in fact that the antiferromagnetism lives off. And what I want to make the argument is that when one has a system in which you have some parameter where you can which you can vary in various ways, compositionally or otherwise, where you're trying to maximize TC, then you almost always seem to have a competing phase that's of a kind of localized nature, and that this phase, in fact, gets gapped by the superconductivity. And so this disparate local, delocal, if you will, in general terms, situation that the material finds itself in, has its problem solved by the material becoming superconducting at sufficiently low temperature. This is true, for example, in this generic Coupe phase diagram. As far as I know, that the pseudo-gap phase does not survive below this DC line. And I'll give one other example here from the old days of the Martensitic transformation and what were considered high TC materials in the old days, A15 superconductors. And the situation, this line here is the superconducting transition temperature of vanadium-3 silicon to vanadium-3 silicon. And this line here is a so-called Martensitic distortion. This represents a lattice distortion of this cubic lattice into a tetragonal state. This has been examined. Hans Otto has examined what happens beyond this point here, and that it is not lattice distorted below this point. So ask yourself, how is it that the Martensitic transformation, there's essentially down here a coexistent state, if you will, of a lattice distortion plus superconductivity that does not exist beyond this point. What's that? How can superconductivity quench, if you will, this distortion? The way it can quench it, it seems to me, is that in fact that the electronic degrees of freedom that are so involved with the superconductivity, in fact, get gapped, if you will, by the superconductivity, just as in the other cases. So, then these short remarks, or maybe not short enough, I don't know, that it seems to me that this situation is holding across the whole spectrum of superconducting materials, that if you will, that there is this termination of the more localized phase, in quotes, where it intersects, where it hits the TC boundary, it does not extend into the superconducting phase. The highest TC is found in proximity to this localized phase, and this is just what's meant by localized here. And so it strikes me that what you have going on, probably in all these cases, is what in the old days when I was growing up was called highly non-adiabatic physics. In the electron phonon case, is that the so-called Born-Oppenheimer approximation just wasn't going to be very good there. I could see no other sort of way in which the Martensitic transformation then could be taken out by superconductivity. Okay, that's my, how do you say, to set up something for debate or whatever.
Okay, so the floor is now open.
I just wanted an opinion on an idea that's floated around, which is that if you could make the iron-based superconductors mount-like in the ground state, that would increase the chemistry-like aspect of them. I just wanted to know, there's been some discussion that if you could make the iron-based superconductors more mount-like, you know, and more chemistry-like, physics-like, together competing phases, there's some feeling that that's going to raise TC because of the competing phases. Do you have a feel for that? Do you want to make the ground state more localized?
Well, no, you want to, I mean, sort of, my feeling about the von Kerker point is the systems on Morbida. And you have these very disparate states that are involved. And that but the superconductivity is living off, in some sense, of this conflict. And sorry. Is that for me?
I got much more interesting
My brother. Yeah.
Yeah, isn't it really a question of a bath of entropy, of degrees of freedom? That in each of these cases you've got some degree of freedom which provides entropy which can either go into the condensation entropy or into the competing state of competing order. And so one of the things we have to learn is how is it that the degrees of freedom that are competing can form a pair, can form a superconducting state. Presumably not all competing states of order can transmogrify themselves into superconductors.
Okay, I mean, you know, what people say is special about the fermions or Coop rays is that the electrons, so to speak, contain the interaction that you know, what's condensing contains the interaction. So in some sense, the things are modified by the opening of the gap. So that the superconductivity, I mean, one of the arguments for the heavy fermion case is that the superconductivity, that the low energy fluctuations, the argument Doug Scalapino makes, the low energy magnetic fluctuations are hostile to superconductivity. So in fact, the superconducting state in 115 has gapped out the part of the interaction that's hostile to it.
But maybe I didn't mean. It seems to me that in all of these cases, the degree of freedom that's competing, whether it's a lattice distortion or a spin degree of freedom, somehow becomes incorporated into the condensate. So part of the issue is to understand how the condensate wave function can incorporate that degree of freedom.
Well, okay, well, maybe let me not answer your question in another way. I mean, just making a remark about, you know, for instance, in the A15s, that, for instance, you have these kind of linear chains of silicons, and it's kind of a chiral distortion. That's what's going on there. But this is deeply involved with the electronics or charge fluctuations associated with that, so that the distortion plus the electronics is part of one complicated entity, right? And so that's exactly what. And so this is where the problem doesn't separate. And that's the only remark I was making. It's sort of a non-separable problem, which makes it interesting but hard to solve, theoretically, apparently.
Okay, I'm new to the discussion. Jim, over there.
So I remember once when we were brainstorming to try to write an ICAM network proposal on this kind of stuff, and I think it was you, Pierce, and people around you were thinking, here's the heavy fermion system where apparently you can get, it is essentially a system with a very small Fermi temperature, and you can get all the entropy to go into the superconducting transition. And you said, well, what if you could do that in an ordinary metal where you have a really high Fermi temperature, and you get all of the associated entropy of the electron gas to go into a superconducting transition. Wow, what a huge transition temperature might be implied by that. And so we were searching around for ways to take the insight from the heavy fermions, you know, over to a system where we could drive T-C up. Well, somehow what seems to happen is that when you go over into the more normal metals, you pass over to using the phonons, and those aren't the right fluctuations to accomplish this goal of getting the Fermi gas entropy into the superconducting condensate. I mean, I'm just fishing around and trying to remember the things you guys were trying to tell us at the time. Maybe you can do a better job than I have in saying that idea.
throwing it back to me. No, I think this is all part of the DF connection that we would all like to see. You can go from 4F, and you can push the energy scale up by a factor of 10 in 5F, and TC goes up to 18 Kelvin. And then you'd like to believe that if you could push the scale up by another factor of 5, which you can in terms of the electronics, you might be able to do the same thing with the TC itself. And somehow what happens is that TC falls away from that scale.
But it's in part maybe it's because it switches over to a different glue. And now we're looking at the phonon entropy, which was kind of what Zach seems to be saying in his Martin-Zittig analogy. So we've lost the glue from the electronic system because we somehow switched over as we drove the Fermi temperature up. And then we lost the benefit that we thought we had, and it's so interesting back in the electron, in the Fermion system.
Thank you.
Wait a second.
You want to go first?
No, I just wanted to give a sign that I'm actually here.
Okay. The cold atom people are very excited about the fact that they're able to look at superconductivity. Are there questions that one could ask in those systems that would help motivate the friction materials?
It's not something I thought about, but maybe somebody else can start with it. I mean, I would imagine that I'd be surprised if there weren't such, but that's it.
And you know, because in principle, they can design design all of this, and then I thought that maybe one could ask some questions about energy space.
Well, I mean, what you run into is instability, right? And so, that if you have these rather disparate possibilities, two ways the system can go, a cold atom system, how do you control that? And you might think of it, get away from it rather fast, which is also a decisive problem in, scaling up from 4F to 5F to 3D, is that in fact, the systems are much harder to control because the instabilities of there are ways in which you can the system control that just take out, if you will, the superconductivity.
Well, you probably noticed that some of the observations that I was pointing out are going just along those lines, that you have ordered phases that are being significantly disrupted by the onset of superconductivity, just along the way it's described. In response to Jim's comment about, couldn't we just use the conventional superconductors and maybe boost their entropy or their temperatures, transition temperatures? Maybe it's useful to look at a counterexample where all this doesn't work, which is the borocarbides, where you have magnetism that's entirely indifferent to superconductivity, except for trivial vortex lattice stuff, which one can understand. And the reason is simple, because you have magnetism coming from one part of electrons, and superconductivity due to presumably electron-phonon interaction coming from a completely different part of electrons, and they just don't care. But when the collective mode that is ordering is made of fermions that are also the ones that are forming the BCS wave function, then, and probably only then, do you get a competition of phases that goes along those lines, like in the iron arsenides or what you have here. And I don't quite know, maybe the last comment, why there's anything non-adiabatic about all of that. For example, the things I was mentioning were trivial mean field stories about Ginzburg-Landau's series of competing order parameters, yet where the ordered states are of the same electrons. But there was nothing non-adiabatic in the entire story, even though these phases had very subtle influence on one and another.
Sorry, isn't the point, however, that somehow the superconductivity precludes magnetism, but magnetism doesn't even preclude superconductivity? superconductivity. So if
Well,
I
that's
write down against Landau theory, the kind of theory you wrote down was basically symmetric between the two.
It wasn't. It was only at the particle hole symmetric point,
Well,
because
but
that's the one. Yeah.
But generically, I would have expected to find just as many situations where the first order line.
No, there's
that
not.
way than the
The
other.
reason is because superconductivity happens to get the entire Fermi surface, while magnetism does so only in very fine-tuned situations.
So you have to focus on microscopics and not.
Yes, you do. I think so.
Well, I mean, but your boron carbide point is there's a world of difference between conductive ions in the lattice and localized moment. You know, it has to do with whether or not, I mean, it's like two, you know, a couple inhabiting the same house,
Right.
a couple being married.
In some cases.
Same thing.
In some cases.
Just to respond to your, in just about all the cases that Zachary has mentioned, and probably true for the Nictites also, the electronic behavior is non-adiabatic in the sense that Landau's adiabatic argument for the Fermi liquid fails. You do not have a strict Landau Fermi liquid for the normal state, I think, for any of these materials.
You're saying independently you realize it.
Yes.
Okay,
Okay?
I see. Mm-hmm.
Any other points? I think this would be a good point to end early, and we will reconvene at 2 o'clock for this afternoon session. Thank you.